Dear students, welcome to another lecture of control systems. In this particular lecture, we will be discussing about the analogous systems. So we will see that what are the analogous systems, and we will also try to understand the various analogy in control systems like force voltage analogy, force current analogy, torque voltage and torque current analogy, right? So to start with, what is an analogous system, right? So we can say that two systems can be analogous to each other if they satisfy the following conditions as mentioned here. That is, these two systems are physically different. That means they are of different types, right? Secondly, when we model such systems, that is when we represent or express such systems through mathematical modeling, their differential equations should be same, of similar type, we can say, right? So these are the two conditions for two systems to be analogous. For example, in electrical and mechanical systems are such two physical systems which are different from one another. Okay, so we can say that we can, set a particular analogy between electrical and mechanical systems. Okay, so as far as electrical analogies are concerned, so since we have two types of mechanical systems, we have translational mechanical systems and we have rotational mechanical systems. So for such two types of mechanical systems like translational and rotational, for translational we have two types of analogies, that is force voltage analogy and force current analogy. Similarly, for rotational mechanical systems, again we have two types of analogies, which are torque voltage analogy and torque current analogy. So let us try to understand all these one by one. The first one is force voltage analogy. What is force voltage analogy for translational system? So in case of translational system, the force and voltage, force is the mechanical quantity, voltage is an electrical quantity. So we can say that these two quantities, that is force and voltage, these two quantities are analogous to one another, right? They are equivalent to one another, but are in different systems. They are in different physical systems, right? But they are equivalent to one another, right? So in this, what we do is the mathematical equations of the translational mechanical system, these equations are actually compared with the mesh equations, that is KVL equations of the electrical systems. That is, we derive the equations of translational mechanical system, and similarly we derive the mesh equation of the electrical system, and then we compare these two equations, and then we find out the electrical equivalent parameters of all the mechanical parameters, right? Such we that since like we have force voltage, so force is a mechanical and voltage is an electrical quantity. They are equivalent to one another but in different physical systems. Now let us consider a mechanical system as shown here. In this particular system we have a mass, then there is a damper, this is damper, this is a mass, a body with mass m, and this is the spring, right? So m is the mass of the body. Okay, similarly k is the spring constant and b is the friction coefficient, right? So now when a force is applied on this body of mass m, it gets some displacement which is x, right? So it gets displaced downward, right? Now let us try to find out its mathematical equation. Okay. So in the system which is shown in the diagram, okay, so there are two types of forces which are acting upon. So two types of forces. So these are external force, which is Ft in this case, and forces resisting the motion, right? So now the forces resisting the motion are, first is inertia force. This is because of the mass, which is given by minus md square x by dt square. This is, let us, equation number 1, right? Similarly, then we have damping force, which is, let us say, f dt, which is minus b dx by dt. This is, for example, 2. And the third one is spring force. This is, let us say, fkt, which is equal to minus kx. This is 3, right? So now as per D'Alembert's law, or D'Alembert's principle, right? Ft plus fmt plus fdt plus fkt is equal to 0. Or we can say that ft minus md square x by dt square minus bd x by dt minus kx is equal to 0. So we can say that it is simplified as ft is equal to md square x by dt square plus bd x by dt plus kx, right? So this is the equation. Let us say this is equation number 4. Okay. So now we will consider a new circuit diagram just to find out. Now in this equation, if you see, all these parameters are mechanical parameters. Now let us try to find out the equivalent electrical parameters. So let us consider an electrical system which consists of resistance, inductance, and capacitor, all are connected in series to one another, right? In this, the input voltage is V and the current in the mesh is I. So this is the circuit, right? Okay, so if we have to write the mesh equation of this circuit, so the mesh equation is V minus R I minus L d I by dt minus 1 by C integration I dt is equal to 0. That is, as per KVL, the algebraic sum of all the voltages in the given mesh is 0, right? So that simply means we have the dynamic equations here, right? So now if we replace, if we replace I is equal to dq by dt, this is, let us say, for example, equation number 5, right? In equation 5, so we get, so let us see what do we get. So it is V minus R dq by dt minus L d square q by dt square minus 1 by C dq by dt into dt is equal to 0. So this is cancelled out here. So we have v is equal to r dq by dt, r dq by dt plus l d square q by dt square. This is q, right? And then we have plus 1 by c q. So this is the equation, right? 1 by c q. Okay. So now this is, for example, equation number 6. Let us say this is equation number 6, right? So if we compare equation 6 and equation 4. Okay, so now we can write the equation 6 and 4. V is equal to LD square Q by dt square plus R dQ by dt plus 1 by CQ, and that was FT is equal to, right, F, this is M d square x by dt square plus B dx by dt plus kx, right? So now compare these two. If you compare, if you see here, so you can easily observe that voltage and force are the, these are something which we call as input, right? Voltage is input in case of electrical circuit, force is an input in case of mechanical systems, right? Then you can see the nature of the equation. This is a second order differential equation. This is also second order differential equation, right? Now, if you see, you can compare the second power with the second power, that is L and M are compared, R and B can be compared, 1 by C and this is compared, right? So now let us see when we compare these, so what do we get? Okay, so now before proceeding to that part, let us consider the torque voltage analogy. Now in this, let us have the mechanical system, which is rotational mechanical system, and let us try to find out the electrical equivalent of the rotational mechanical system, right? So a rotational mechanical system is generally represented by this particular diagram. Okay, so now here we can use the torque equation. So we need to find out the torque balanced equation, right? So the torque balanced equation can be obtained by equating the torque that is given as an input to the torque that is coming as an output to the system, right? So in this particular torque, in this particular system, we have external torque and then we have torques resisting the rotations. So external torque here is, let us say, TT, and these are the two parameters which are like inertia torque, second one is damping torque, third one is spring torque, right? So we have all these torques here. Inertial torque or inertia torque is given by, it is, let us say, TIT, which is equal to minus J d square theta by dt square. Similarly, the damping torque is TDT, which is equal to minus b d theta by dt. Spring torque Tk T is equal to minus k theta, right? So these are the equations for second order rotational system. Now let us apply the Lambert's law here. Okay, now um, for a torque balanced system, T T plus T I T plus T D T plus T K T is equal to 0, right? This is as per D'Alembert law. Now T T is equal to, then if we substitute all the values, right? So once we substitute all the values T I T, it is J. If you substitute here, J d square theta by dt square minus T2 TD. This is TD. So TD is minus b d theta by dt minus k theta is equal to 0. So T is equal to j d square theta by dt square plus b d theta by dt plus k theta, right? Now this could be, let us say, your equation. You can assume it as an equation. Okay, so if we go previous on the previous slide, we'll see that the equation they have taken is, the last equation is 6 here, right? So we can assume that equation as 7. So now this is, for example, equation number 7. Now compare equation 7 with which equation? You can compare this with the electrical quantity, right? So if you compare this with the electrical quantity, so what is that quantity? So it is here, right? So we can write V is equal to R dq by dt plus N d square q by dt square plus 1 CQ. So it is equal to, the voltage is equal to, right, R dq by dt plus L d square q by dt square plus 1 upon C Q, right? So these are the equations, right? So this is, let us, equation number 8. Okay, now with 8, right? So when you compare, so you'll get some analogy here. So okay, so that simply means we simply have to compare the equation, right? So now this is the force voltage analogy. In this you can see we have translational systems. So this is translational actually. Then we have electrical systems, right? In translational system we have force, but the equivalent, electrical equivalent of force in electrical system is V. Similarly, mass and inductance are electrically correlated. Frictional coefficient and resistance are correlated. Spring constant is equal to reciprocal of the capacitance 1 by C. And displacement is charge, velocity is current. So these are the analogous quantity. That is, the analogous quantity of force in electrical system is voltage. The analogous quantity of mass in electrical systems is inductance, and similarly, the analogous of velocity in electrical system is current. Similarly, we have torque voltage analogy also, right? In torque voltage analogy, you can see that torque is equivalent to voltage. Moment of inertia, instead of mass, we have moment of inertia, which is equivalent to inductance. Then the rotational friction coefficient. So this is equivalent to R only. Torsional spring constant is reciprocal. angular displacement, angular velocity, right? So we can say from this analysis, we can say that the mechanical systems are analogous to the electrical systems, and we have two kind of force and so voltage analogy, force voltage and torque voltage, right? So similarly, we can have the force current analogy and torque current analogy. Now, what is force current analogy? So force current analogy is basically the analogy in which the mathematical equation of the translational mechanical system are compared with the nodal equations of the electrical systems. That means, again, we will take an electrical system and we'll take a mechanical system. The mechanical system is translational mechanical system, and the electrical system is the one in which all the branches are connected in parallel. That is, all the elements are connected in parallel, right? So it is shown in the diagram here with RLC. So the nodal equation in this case will be, what will be the nodal equation here? So the nodal equation here will be, if you write, okay, so we can apply KCL here, okay. So using KCL, right? If we use KCL here, what will be the nodal equation? That is the question now, right? So if we apply KCL, so we'll get I is equal to E by R plus 1 by L integration E dt plus C dE by dt. This is one equation, right? Now, if we see that in this particular type of system, we can say that the flux phi is basically the a parameter which is related in this particular analogy. So phi is equal to integration E dt. So if you see this and you rearrange this one, so you'll get E is equal to dq by dt, d phi by dt, sorry. Okay, so E is equal to d phi by dt. Now if you substitute it here, so your I will be equal to 1 by R d phi by dt plus 1 by L phi plus C d square phi by dt square. So we can rearrange this one again. So it is C d square phi by dt square plus 1 by R d phi by dt plus 1 by L phi. So this is some equation, right? So now if you compare this equation, if you see this equation, and if you compare this equation with the equation force is equal to m d square x by dt square plus b dx by dt plus kx. If you compare these two, so you will get a kind of analog. You can see that here force and current are analogous to one another. Mass and capacitance are analogous. Friction coefficient 1 by R analogous. K and 1 by, this is 1 by L. They are analogous to one another, right? So we can see it here, right? So as you can see, this is the force current analogy. So in force current analogy, you can see force is equivalent to current, mass to capacitance, frictional coefficient to reciprocal of resistance, spring constant to reciprocal of inductance, displacement with magnetic flux, and velocity with voltage, right? Similarly, if you compare, this equation, this current equation with the standard torque equation here, right? So we have a torque equation here, right? Torque J d square theta by dt square, this equation number 7, right? So if you compare equation number 7 and let us say this is, for example, equation number 9. If this is an equation number 9, right? If you compare 7 and 9, even then you will get a kind of analogy, right? So that is called as torque current analogy. In torque current analogy, torque and current are analogous to one another. Moment of inertia and capacitance are analogous to one another. Rotational friction and friction coefficient and reciprocal of resistance are analogous to one another. Torsional spring and reciprocal of inductance are analogous to one another, right? So in this way, we have angular displacement and magnetic flux, angular velocity with the voltage. So in this way, we can determine the analogous systems of electrical and mechanical systems, right? We can say that electrical systems are analogous to mechanical systems and mechanical systems are analogous to electrical systems, provided that their mathematical equations, that is, if we model such equations and we derive the mathematical equations of such system, these equations should be of similar type. Means you can compare a second order equation with a second order equation or a first order equation with a first order equation, right? So in this particular lecture, our objective was to understand the analogous systems. Our objective was to see that how many analogies are there, right? We have seen that there are 4 types of analogies, right? Which are force voltage, torque current, torque current analogies, right? Okay, so now this is it for today's lecture, guys, and thank you so much.